Hey, this is the last hour of Physics 1C for October 27th. We're now going to move into talking about the negative sign of Faraday's Law, which we call Lenz's Law. Lenz's Law. I'm going to write in words what Lenz's Law says, and then I'm going to show you some examples so you can get an idea for how it works. Okay? So Lenz's Law states that it's all about the direction of the induced EMF, okay? So the direction of the EMF induced in a loop of wire is opposite to the change in flux. That is kind of the probably shortest way you could say it. The direction of the EMF induced in a loop is opposite to the change in flux. That's one way you could say it. But there's a better way to say it. Okay? The better way to say it would be to add in a line here. Okay? So this is true, but I'm going to add in a little paragraph here. The direction, not a paragraph, it's just like a short statement. The direction of the induced EMF in a loop is such that the magnetic field, what we call the induced magnetic field, points opposite to the change in flux. Now, I personally think that the words themselves don't really do justice to what's going on here, so I'm going to put it this way. Let's drag these pictures from your textbook here. We'll start off with those, and then we're going to do some kind of like I'm gonna give you guys some examples to test for yourself if you understand what this means. All right, so this is the picture that shows up in your textbook. Some version of this shows up in any textbook that discusses this, and the one in your book is okay. It's not 100% perfect, but there's only so much you can do with a two-dimensional picture. Okay, so this is showing the directions of induced currents as a bar magnet moves along the axis of a conducting loop. If the bar magnet is stationary, there's no induced current, okay? There are four possible scenarios here, okay? Scenario one, the magnet moves downwards. The loop is this way, okay? Now notice on each of these pictures, there are two magnetic fields. There is a blue magnetic field coming from the magnet. You can see it emanating out, right? And there's another blue magnetic field called B induced. And that's the thing I want you to focus on, is this induced magnetic field, because that's the key to understanding Lenz's law. When the magnetic field goes down, I'm just going to ask y'all what happens to the flux through the loop, the magnetic flux, when the magnetic field goes downwards? Does the flux through the loop increase or decrease? Does the question make sense? It increases, right? So if the flux increases, and directly beneath here I'm going to write Faraday's law. Faraday's law tells us the induced EMF is opposite to the change in flux. You also have to multiply by the number of loops, but the induced EMF is opposite to the rate of change of the flux, okay? So in this case, the induced magnetic field is opposite to the external magnetic field. Can everyone see that? So if flux goes up, B induced is opposite to the external field. That's one possibility. If the flux goes up, B induced is opposite to B external. Can you see that in this picture here? Now, if B induced goes up, then you point your thumbs in the direction of B induced, and your fingers are going to sweep out with your right hand the direction of the current. Does that make sense? So that is your induced current right there. Okay. What's the opposite to this one? So we'll look at A first. We just described that one. The exact opposite of A would be C, right? What happens to the magnetic flux through the loop if the magnet moves away? Does the flux decrease or increase? Those are the only two possibilities. When the magnet moves away, what happens to the flux through the loop? Does it decrease or increase? Decrease. Right? It's going away, right? That's what happens in this picture here. Flux is getting smaller. There's less lines. Flux is getting bigger. Flux is getting smaller. Right? Okay. In that case, if the flux decreases, if the flux goes down, then B induced is same direction as B external. Okay, those are the two possibilities. It's either this one, when the flux goes up, the induced magnetic field is opposite. When the flux goes down, induced magnetic field's in the same direction. And that's it. That's what Lenz's law says. Those are the two possibilities. So in this picture, right here, in B, the magnet moves away, so the flux decreases. If the flux decreases, the induced magnetic field points in the same direction. And a magnetic field that's induced in this direction means the current has to flow this way. It's kind of complicated. But once you figure it out, I think you'll get it. Like once it kind of sticks, I think it sticks pretty well. Does anyone have any questions? We're going to do some exercises to get you comfortable with this, but anyone have any question? So my rules for this are, I take my thumb, okay? I point it in the direction of the external field. In this case, my thumb would point downwards. My thumb would be pointing like this, okay? And then here's my fingers. So I start off, I point my thumb down, okay? My right hand. You know, it's my right hand actually, so I think I should draw this on the opposite side. So my thumb's pointing this way. So there's my thumb, and then here's my fingers. So that's what I do. I start off like that. I point my thumb down. That's the external field, right? And then I ask the question, is the flux increasing? If it is, you flip your thumb upside down, and that's the direction of the induced field. If it's not, you leave your thumb pointing in the same direction, and that's the induced field. And then you sweep your fingers in the direction of the current. That make any sense? That make any sense at all? We're gonna try some examples, okay? I'm gonna have you all answer in the chat to tell me what you think the answer is. Okay. So here's this is another document that I found from another website that has some nice diagrams. I also pulled some things into this OneNote thing, but I could link this to you too, so you can look at it yourself. So induced current is such as to oppose the change in flux within the circuit, right? Okay. So here's an example. You have a conducting loop. You have a magnetic field that points into the page, okay? The conducting loop falls downwards through the field as shown. We want to find what is the direction of the current induced in the loop as it leaves the field. Okay? So I'm just going to ask you the same questions I asked a second ago. What is happening to the magnetic flux through this gray loop here? Is it increasing or decreasing as it goes out of the field? Decreasing. If we know that it's decreasing, all you have to do is point your thumb in the same direction as the magnetic field, your right hand. Point your thumb into the page, and then your fingers will sweep in the direction of the in the direction of the current. Can you all type in the chat? Is the current clockwise or counterclockwise? What do you think? Clockwise? Does anyone think it's counterclockwise? That's right. The answer is clockwise. Okay. So again, the way you do that is you say the flux is decreasing. When the flux decreases, you point the thumb in the same direction as the field. Okay. So decrease, same direction. If it was increasing, opposite direction. Okay. So now what if we do the, I don't want to, what if the loop started like up here and it moved from this position down to here, but it didn't leave the field? Does that question make sense? What if it was something like this? Okay, you figured it out. That's right, Mayars. It's no change. So say I've got a field like this, and let's say that it occupies this area of space. And we ask the following 3 questions. So let's say I have a loop here, of metal loop, and it moves from there at point A, and it moves over here to point B. And let's say that that magnetic field is uniform. No change, right? If the magnetic field is uniform and the loop moves from here to here, the flux doesn't change. What does that mean about the induced EMF? If the flux doesn't change, and Faraday's law says you need to have a change in flux, what does that mean about the induced EMF? It's 0, right? So in this case, when you do this, the current would be equal to 0. However, if the loop goes into or out of the field, as we just saw, okay, so another possibility would be the opposite of what we just saw. Say the loop starts off here, and it moves in this direction until it's right here. What now? What's the direction of the induced current going to be? Is the flux increasing or decreasing? That's the first question. The first question is the flux increasing or decreasing? Flux increases, right? Okay. In this case, flux is increasing from here to here. That means that the induced magnetic field needs to point opposite. So I'm just going to draw right at the center of the loop here. This is going to be the direction of induced magnetic field, right? Now, if that's the induced magnetic field, what direction does the current need to flow? Does it need to flow this way, or does it need to flow this way? Just point the thumb of your right hand out of the screen and wrap your fingers in the direction the current's going to flow. Is it clockwise or counterclockwise? It's counterclockwise, that's exactly right. In this case, your induced current is going to go this way. Because the flux was increasing, so the induced magnetic field is opposite. On this picture, not this picture, on this picture, where the loop goes out of the field, we said the answer was that the current is going to flow clockwise, right? So it's consistent, right? When it goes in, the current is clockwise. But if that same loop were to go from, let's say here, we'll call this point C, and it moved from here to point D, okay? Here we would say if its flux is decreasing, then our induced magnetic field is the same direction, and the current flows the opposite direction. as it was before, but it's in such a way that it corresponds to this. Okay. All right, that's kind of like the general setup. I'm now going to just show you these and ask you to make a guess for yourself. All the answers for these are at the bottom, by the way, in case you don't believe me. But we just did this one, right? So I want you to say in the chat, the conducting loop enters the magnetic field. What is the direction of the current induced in the loop as it enters the field? Counterclockwise? Everyone agree? If you're not getting it quickly, it's totally okay. This is kind of tricky. But yeah, counterclockwise, such that the induced magnetic field would be pointing into the loop. Thereby, you get the current. Okay, this one's a little different. It says an induced... Oh, here we go. You don't have to keep reading this, I guess. Circular wire loop sits inside a larger circular loop that is connected to a battery. So here's our battery. The long lines here mean that this is the positive side. Okay. And that's the negative side. So the current's going to flow this way. We're interested in what happens with the blue loop, though, that's inside of it. We want to determine the direction of the current induced in the inner loop when the switch in the outer circuit is closed. What do you think? Take some time. Wait, what's going on here? Okay, let me actually like put this into OneNote so we can do some things. Yeah, you guys are confused. I understand. Okay, I understand. Let me put this into OneNote and we'll talk about it. I considered putting all these in OneNote earlier, but wasn't sure. Okay, so what happens to the current flowing through the black wire when you close the switch? What happens to the current? We throw the switch this way. What direction does the current go? It goes around this way. So that's our current, right? In the outer loop. Right when the switch is closed, that's what happens, right? Okay, so now we've got this loop, and it has current, right? But you all know that a wire that carries current produces a magnetic field, right? I think the Dodgers must have just won the World Series. People are screaming outside. People screaming around your guys' homes. Yeah. I was hoping I could finish class before that happened, but that's okay. Fireworks. Yeah, I hear a lot of fireworks going off too. That's awesome. That's really good to hear. All right. They've been so many times in the last few years. They keep losing, so yeah, that's awesome. All right, so that's the direction of the current, right? And yeah, that produces a magnetic field as well, right? What direction does when you have a loop of wire like this, what kind of magnetic field does it produce inside of it? Into the page, yeah. So now we've got a magnetic field into the page. So here's the question. When it was open, what was the magnetic field? 0, right? When we close it, all of a sudden there's a magnetic field, right? So did the flux increase or decrease? Yeah. All right. Does that help you to answer the question? Now that you know that? What direction will the current in the blue loop be induced? opposite, right? It has to be basically opposite to this current, right? Because it has to produce an induced magnetic field that's opposite. There's a few steps to that, right? It's not just like super simple. Like you have to go through each of the steps to get there. Yep, that's right. Flux increases, so the induced magnetic field must be opposite to the external field. Counterclockwise. Yeah, that's right. Does that make sense? Okay. It's kind of tricky, right? It's not easy. But it is where am I going? It's right here, right? Okay. We'll do a few more of these. How about this one? This one actually has a magnet. Drop a magnet south side down. Okay. What's the direction of the induced current in the loop going to be as it goes from here to here? One thing I should say about this is you can consider the magnetic field of the magnet to basically point straight up. People really saved up the fireworks for tonight. Going wild over here. It's upsetting your dogs. Field is induced downward, so you think the clockwise current. So you're saying that, so again, I just to give you a hint here, this is basically the external field. Okay, it goes this way. So when it falls through the loop, we're going to need to have, the flux is going to be increasing, right? So we need the induced magnetic field to go the opposite way. Like that. In order for that to work, the current's got to flow around like this. Again, it's opposite. Yeah, clockwise. Can everyone see that? Okay. I'd like to do some problems before we go that have numbers in them and stuff, but this is Lenz's law. And you can use that little document. I linked it in the chat to solve some more problems here. So you've got one like this, another one like this, another one like this. This one has a variable resistor. So there's just little changes, okay? This one is really impressive. God, I wish I could show this to you. If you hang, think about this for a second. Actually, I might as well just show you the video that goes along with this too in a second. So suppose that I take one of these loops that we've been talking about here, right? And I hang the loop up like this, right? And then I take a magnet and I push it towards it, right? We just learned that the wire basically is going to set up an induced field that's opposite to the magnet, right? What's going to happen to the wire then? If the wire suddenly has an induced current that's opposite to the magnet, is the wire going to be repelled or attracted? What do you think? Remember that it's going to set up a field that's opposite to the magnet, right? Well, opposite they attract, but one second, let me what direction in this case? I gotta actually draw this on the board real quick. One second. All right, so for this one, Okay, let's go through the same process again. The external field is this way, right? Flux is increasing, so the induced electric field, or sorry, induced magnetic field has to go this way. The wire moves to the left. If the induced field goes this way, it's as if... It's a repulsive, you get it, that's right. It's as if this wire suddenly acts like a magnet that's facing this way, with the north end here and the south end back here. It turns the loop into a little dipole magnet. And now there's going to be a force this way. That's a cool demo you could do if you got a little loop and you can hang it somewhere and yeah. The cool thing is, when you push it in, it's repelled. When you pull it out, it's attracted. It's kind of a little energy conservation thing going on there. You push it in, you see a force outwards, you pull it out, and then it's attracted. Because the loop will always do the opposite. It'll always do the opposite. Okay, we gotta do at least one of these problems so I can prep you to be ready for your homework. We will get to some more of this stuff, I guess, next time, regardless. But I do want to do one problem, and then I want to show you another video. Here, let me figure out. We're really far down here. What's a really good one to do? I guess this is the best one because it's going to cover the majority of your problems here. So let's do this one. I almost want to draw my own picture, but we'll use theirs. Their picture's fine. Okay, here is one of the simplest applications of Faraday's law. Your book calls it a slide wire generator. Your book also refers to this as motional EMF. I hate the way that they put so much information into the picture. It doesn't allow much for the student to figure out. Okay, so we got a picture like this right here. I feel like I'm just going to end up redrawing this anyway. The picture is as following. We have a U-shaped bar here. Here, let me... There we go. We'll answer these other questions later. We've got a U-shaped bar right here. And fitted in between them, you have a bar that can slide right here. So this bar can slide to the right. And it slides from this position to a position directly to the right of it here. Okay? Now, we're interested in calculating what the induced EMF is. And the idea will be here that the wire moves with a constant velocity to the right. Okay? See if you can convince yourself the direction of the current here is proper. So what's happening to the flux through this loop? The loop would be this loop right here. The wire moves to the right. What's happening to the flux through the loop? Is it changing? Is it not changing? What's going on? It's increasing, right? Why is it increasing? Which of the three factors is causing it to increase? Is it the magnetic field, the area, or the angle between the two? It's the area, right? The fact that the area of the loop gets bigger means that the flux through the loop increases. Yeah, this is where I think if I had drawn the picture myself, it might make more sense. Let me just I can't avoid it. So we've got magnetic field, right? Embedded within this magnetic field, we have a wire. Let's use this color. And the wire is shaped kind of like this little U right here, okay? That's a wire. On top of this wire, you're going to place a piece of metal, okay? So I take a piece of metal and I place it on top of the wire here. This metal is going to make electrical contacts at this point and this point here, okay? So this is like a piece of metal bar, something like that. Now what we do is we pull the metal bar to the right with a constant speed. All right? It eventually moves to some position right here. My loop is this here to begin with. And then it's this bigger loop that's twice as big to end with. So the area went from A to like 2A or something like that. The area increased. And therefore, the flux also increases. Did that help to clarify what's going on? You pull it to the right. You pull it from here to here with a string or something, so there's a force that you're applying this way, it pulls the rod from this position to this position. The flux increases. Now, if the flux increases, what does that mean about the direction of the current? It should be in such a way that it produces an induced magnetic field that's opposite to this one. And that means that the induced magnetic field has to make it so that the current flows this way, counterclockwise. Flux is increasing, so your induced magnetic field has to come out of the page. And that means that the current's going to flow this way, and this way, and this way, and this way. Does that make sense? Tell me why that is, Mr. Miars. Why would it make no sense if the current went the other direction? Yeah, I think that's kind of what's confusing about the picture, actually. Yeah, the current doesn't actually show up until you move the wire, by the way. Does that make sense? The current is only there in this problem when you actually move it. I knew I shouldn't use this picture. I knew this would be confusing because it's just there's so much information here. I needed to set it up better. I guess I'll try to remember that for next time. The advantage and disadvantage of having the ability to directly copy the problems in is that in a classroom, I'd have to stand at the board and I'd have to draw a picture and I'd have to set it up for you. And I think within that setup, there's a lot of value. Because just giving you the picture like this, I think is problematic here. Well, our goal is to find the EMF, okay? So I'm going to try to go through how we can do that here. I believe this would be pretty useful to a lot of the problems you're going to do here too. So our goal is to find the EMF that's induced and the current as well. All right, we're going to use Faraday's Law. Faraday's Law says we're going to just look at the time rate of change of the flux. In this case, there's only one loop here. That means we need to take the time derivative of B times A times the cosine of the angle between B and A. Okay, what's A? Well, A you can see here is pointing into the page. The area vector is pointing into the page. The magnetic field is also pointing into the page. That means the angle here is going to be 0. All right. The magnetic field is actually something that's not changing in this problem, so we're going to pull that out. So we end up having to do the derivative of the area with respect to time. And I'll leave this negative sign on here just for good measure. So it's the rate at which the area is changing that we care about now. And what will that be? Well, in this case, I would argue that if the length of this side here is L, okay, that's basically the length of this side here too, then the area of my loop at any moment will be related to, I'm going to define this direction to be the positive x direction, and I'm also going to define this to be the x coordinate. I'm going to call this to be x equal to 0. So I would say that in general, the size of our loop right here is going to be given as L times the x coordinate, okay? Yeah. So I'm going to say that the flux, or the EMF that's induced now, is going to be B times D times... I'm going to say that the area in this case is just equal to L times x, where this side is x and this side is L. Sorry, I'll use capital L because that's what they're using in the picture too, big L. So the area is going to be L times x. But then I'm going to say that the length L is constant, so that this is going to become negative B, the L comes out, and then I just have dx dt. But in this case, if the velocity is constant, what is dx dt going to be equal to? Velocity, yep. So we end up getting B times the length times the velocity. And there we go. And then the negative sign just means that the direction of the current is opposite to the direction of the flux change. And in this case, that means the current has to flow this way. That makes sense? Just in terms of the equation, I think it makes it a lot more sense to just write it as this, the absolute value. If the bar were to move in the opposite direction, the current would just change directions. And that's basically the idea. You can literally generate electricity by doing this. You wouldn't generate a lot of it, but you could. Does that make sense? Anyone have any questions? If it was rectangular, it'd be the same. I mean, it might change the area, how you define the area, but that's about it. To me, this looks very rectangular, honestly. It's like, it says U-shaped, but it's, you know, it's pretty rectangular. I think it'd work just fine. They're two rectangles. Well, I mean, the way I defined this, I pretty much said it was a rectangle, basically, right? Okay, the next part of this problem says energy is going to be dissipated in the circuit owing to resistance. We want to let the resistance of the circuit be R. We want to find the rate at which energy is dissipated in the circuit and the rate at which work must be done to move the rod through the field. For this one, I am going to draw my own picture. So we'll just do it like this. So I've got a wire, and get rid of this piece here. That's going to be our U-shaped thing. And then I've got magnetic field. So we'll put magnetic field in here. We have uniform fields throughout this region. Okay, that's magnetic field. Again, on top of this, we lay another wire from here. And I'm going to add one piece to this as well that the book doesn't do, just to simplify this. We're just going to put a resistor over here. So in this region right here, I'm going to throw in a resistor. And say that the majority of the resistance of this circuit is made up of that resistor there. Of course, the wires themselves have resistance, but anyway. We're going to say that we're going to be moving this object with a constant velocity in this direction, and that it's being moved by a force that we apply in this direction as well. We're going to call that the applied force. All right. And what we want to calculate here is to find the rate at which energy is dissipated in the circuit and the rate at which work must be done to move the rod through the magnetic field at a constant speed. Okay. So we want to find the rate of energy dissipation, which I think we sometimes call, what's another word for that? For the rate of energy dissipation. Does that sound like any problems we've done in the past? Power, that's right, exactly, that's power. Power. Now, how could I calculate power here? We said that if the velocity goes this way, that it has to produce an induced EMF such that there's going to be a current flowing through our wire, and that current is going to flow this way, right? And in this section here, oh god, that's awful. Oops. In this section here, the current goes up, right? Power, he says V equals IR. Is this why you added the resistor? Yeah. Yeah, that's voltage though. What's power, do you remember? Voltage is IR, and then power was V times I, and there was one that had resistance in it too. Do you remember what that one was? We can do I times V. I'm going to do I times little e, because we've been using E for EMF, right? We'll do that, right? That's our power then. Current times the voltage, right? So what's the EMF? We've already found that right there. The EMF is B times L. I hate writing L's like that. I'm so used to writing curly L's. B times L times V, that was the EMF, right? What would the current be? What would the current be? Can use our Ohm's law equation, right? The EMF is equal to I times R. So the current has to be equal to the EMF divided by R. So we put in here E over R for the current. And then say, oh, we know that E is this thing. So we have B times L times V over R. Multiply that times B times L times V. So we end up getting B squared, L squared, V squared, divided by the resistance. That would be the power dissipated in our resistor. That's the rate at which power comes out. And if you attach a light bulb right here, the light bulb would get bright, right? All right. The other piece of this is to say, does anyone have any questions about this part? That probably doesn't mean very much to you, but if you knew the field, you knew the length, you knew the velocity, you could figure out the power. What does this tell us? It tells us that the power is proportional to the velocity squared. That's what it tells us. The faster we move it, the more power we're going to generate, right? All right. The other piece of this is to find the rate at which the work must be done by this force right here in order to move the rod through the field at a constant speed. Okay? How could I figure that out? How can I get the work? No, I'm sorry, it's not the work. It's the rate at which the work is done. So again, we need power. We kind of need to know, in this case, what the applied power is going to be. What's the external power we need? So if I have force and velocity, how can I get power? Anyone remember that? Force times velocity, exactly. So if I do force applied, and I multiply by the velocity, that's going to give me power. Technically, it's a dot product, but they're in the same direction, right? Okay. How big do you think the force needs to be in order to move this at a constant speed? That's from 1A. Yep. How big does this force need to be in order to move this at a constant speed? Are there any other forces that would be acting on this rod? Maybe friction, sure. There could be some friction here at the rails, right? Here and here. Maybe gravity. We're assuming probably that gravity is pointing down. Like this could represent the top of a table, right? And gravity would be going into the page. So gravity would probably affect the friction, but it probably wouldn't affect the applied force directly. What other force would there be? We're going to say in this version of the problem, we're going to make these approximately 0, but I will say you may see a problem later on in which they're not 0. Just change in area definitely creates a change in magnetic flux. That change in magnetic flux is where the current's coming from, by the way. The current wasn't there until you pulled it, right? What about this bar here? Is it going to feel any other forces? A magnetic force. Which one? Ash, you're right. There is a magnetic force. What kind of magnetic force would it feel? What direction would it go? Which magnetic force would it be? What type of magnetic forces did we learn about in this class? One of them we mentioned earlier was the QVB one, right? What was the other magnetic force we learned about? You got the right answer, Lee, but I also want to know, what is the force itself? Because we're going to need this to prove this. What was the other force we had? Does a wire that has charges inside of it moving have a force on it? Certainly if one charge that's moving alone feels a force, a wire that carries a bunch of charges that are moving should also feel a force, right? Does anyone remember what that equation was? I'll tell you, it has an L in it, if that helps you to remember. Go for it. Feel free to, look through your notes or look at your book, whatever you want. If I give you a wire and I say it has a current I flowing through it, and I embed it into an external magnetic field like this, does that wire feel a force? Yeah, Ty has it right. It's the current times the wire length crossed with the magnetic field. And then the length, does this look familiar now that I write it down? Okay. What direction does it point? I goes up. Use your right hand rule. If I goes up, the magnetic field's into the page. What direction is that force? Left. That's right. So now we have a magnetic force going back this way. Okay, and let's just ignore friction, although that's a silly thing to ignore. The applied force now, how big does the applied force need to be if you want to move this with a constant speed? Does it need to be bigger than the magnetic force? Equal, exactly. It just needs to be equal to the magnetic force. So we can say that the applied force should be equal to the magnetic force, but that the magnetic force we said was just I times L times B. Okay, now we can put this all together for our equation down here. The power that the applied force has is equal to the applied force, but we just said that was equal to the magnetic force, which is equal to ILB. So we put ILB in here, multiplied by the velocity, and then we plug in what I was. BLV over R is what I became, right? From E over R from here. So we have BLV over R for the current, times LBV. But I think what you'll find is that this is exactly the same thing as what we got here. You group the terms together. It's B squared, L squared, V squared, divided by R. So whether we look at it from a mechanics approach or we look at it from a magnetic approach, look at it forces, or we look at it in terms of power being defined as current times EMF, you get the same answer. And what you find is that the power that you put in, this is like the power in to the system, ends up being exactly equal to the power that comes out of the system, which is kind of nice. It's a conservation of energy thing, right? You put energy in, and it causes the resistor to heat up. And the rate at which the resistor dissipates energy is exactly equivalent to the rate at which you're putting energy into the system. Now, of course, if we added in friction, they wouldn't be exactly equal to each other, but at least we would understand that the losses of energy due to friction, or the conversion of energy due to friction, would be the reason why. Does that make sense? Anyone have any questions? So that's a good place to stop, and we're at time or over